Welcome to the Hidden Voltaic Village training grounds, where we get to practice our cell notation. So for this question, it says that we're going to be describing a voltaic cell with diagram and notation. It says, draw a diagram, show balanced equations, and write the notation for a voltaic cell that consists of one half cell with a chromium bar and a chromium nitrate solution, another half cell with a silver bar and a silver 1 nitrate solution, and a potassium nitrate salt bridge. Measurement indicates that the CR electrode is negative relative to the AG electrode. So it's a lot of words that we have to make sure that we're breaking down. A lot that they want from us as well: diagram, balanced equation, and the cell notation. So first, let's go ahead and get our diagram written down so we know what our voltaic cell looks like. And then we're going to spend time, of course, getting our half reactions, then going forward to get our balanced equation, and of course, answering the rest of the question. So to get started, I'm going to write 2 beakers to represent my half cells. Okay. I'm going to have a salt bridge, which is going to be my inverted U tube right there. Then I'm going to have my electrodes. So they told me I'm going to have one, which is going to be a chromium bar, and then one, which is going to be a silver bar. Okay. They also tell me that everything is good and complete. So I'm just going to write a wire here with a little voltmeter. All right. Now, of course, I also have my electrolyte solution. What are my electrolytes going to be for my chromium? Well, they gave me a chromium nitrate here, so I'm going to have Cr3 plus ions here. And then they also gave me AgNO3, so I have Ag plus ions hanging out over here. Now, why am I not using nitrate? Well, we know from chapter 14, nitrate comes from a strong acid, which is nitric acid. So, of course, that ion does not really react or anything like that. And then finally, they said our salt bridge is going to be K plus and NO3 minus. So that means K plus is going to replace the missing or losing positive charge over here, and NO3 minus is going to replace the missing or the help balance out the additional positive charges here. Now the question becomes, well, wait, why did you put chromium here on the left and silver here on the right? Because of this last line. It says chromium electrode is negative relative to the Ag electrode. Because chromium is negative, that means it has to be the anode, since we know the anode is negative. And therefore, the Ag automatically has to be the cathode, which is going to be positive. Okay? So we have our diagram. Great. That's what they want us to do. Now they want us to show the balanced equations. And so therefore, we need to make sure that we have half reactions for each of our half cells. So I'll write a half reaction for our anode here and a half reaction for the cathode here. So for our anode, we know that we're going to have our chromium 3 plus. Since it's the anode, we know it's going to lose electrons. So we're actually going to start with our chromium, which is going to be the solid, which is then going to lose electrons to form chromium 3 plus. How many electrons does it form? 3 electrons that are going to be lost. Those 3 electrons are then going to move through the wire, right, of the electrochemical cell. And I can then say that this is oxidation as well. Now for the cathode, I am going to have my Ag plus and my solid silver here. So we're actually starting off with Ag plus ions, okay? You're going to be aqueous, and I forgot to write my aqueous up here. And then we're going to, again, accept or gain electrons. And so how many electrons are going to be gained? 1 single electron, so 1 electron here. And that's going to help us form Ag solid. And so with this portion here, we're going to have our potassium that's going to replace the Ag plus that is going to, of course, be leaving out a solution to be added to our Ag bar here. All right, folks, looking good so far. But they want us to show the balanced equation here. So we need to make sure that we are balancing out our electron charge here. That means there are 3 electrons that are going to be given up by our chromium. So we need to make sure that there's going to be 3 electrons gained by our Ag plus. We have to multiply this entire reaction by 3. When we do that, that means we're going to have 3 Ag plus here, plus now 3 electrons, which is going to form 3 Ag solid. And when we put all this together to get an overall reaction, which is what they want, now we can go ahead and get rid of the 3 electrons here and just continue to write down everything that's left over. So chromium solid plus our 3 Ag plus, which you know is aqueous, all right? And that's going to be all of our reactants here, so we're good. And then our products are going to be our Cr3 plus, which we know is going to be aqueous here. And then we're left with also 3 Ag solid. So that is going to be our balanced equation. right? Based on what was given to us. So we have that part of our answer. And finally, they want us to write the notation for the voltaic cell that we have here. But before I do that, remember I could write reduction here as well. Okay, folks? So far we have our diagram. We're able to get our half cells just by what was given. And we're able to, of course, get rid of anything that's the same, balance our charge, and get an overall balanced equation, which is what they want. Finally, we'll write our notation based on what's given. We know we're going to start with our overall anode. We're going to have two double lines to constitute our salt bridge, and then we'll end with our cathode. So for us, we're going to start off with our chromium solid here to show the phase change when the chromium loses electrons to produce Cr3 plus ions. We're going to form a single line here. Then, of course, we have our salt bridge, and those 3 electrons are then going to be moving from left to right to the cathode, where our silver ion here is then going to, of course, gain those electrons or accept those electrons. And so we have Ag plus aqueous here. And then, of course, as soon as it accepts those electrons, it's going to form Ag solid. So we have to show a phase change, which is a single line. And then we simply write Ag solid. This will be the answer for the notation. This will be our answer for the overall balance equation. And this will be the answer for the diagram, folks. So as you can see, you kind of mixed a lot of things together, but I think this is a great example because you're able to kind of, again, go back and review what you know from a previous video, and then take your flashcard moments and your notes and start breaking it apart for these type of questions. Now that we have practice with putting it all together, the Raikage wants to have a couple of final words before we move on. The Raikage wants to explain how and why electrons flow in a voltaic cell, kind of as a wrap up to this conversation. He states that in a voltaic cell, like the zinc copper 2 plus cell that we always have been looking at this entire time, the reaction takes place because the zinc is going to act as a stronger reducing agent compared to copper. What does the reducing agent mean? It means that zinc is going to give up its electrons more easily than copper will. And how can we verify this? We verify this by allowing the half cells to be in equilibrium by allowing the switch to be open. When the switch is open and not closed, like we're normally seeing here, when the switch is open, the electrochemical cell is going to be inactive. So therefore, the bar that you see here and the electrolyte solution will become in equilibrium. Just like our bar that we see here and the electrolyte solution will also be in equilibrium. So no reaction is occurring. And what we notice is that zinc readily gives up electrons more than copper, meaning that this zinc bar is going to want to produce Zn2 plus way more than this copper is going to want to produce Cu2 plus, all right? So it doesn't really happen that way, okay? But this portion where this zinc is going to break down as zinc 2 plus, it does happen a lot, okay? And so because of this, that's going to help us understand that our electrons in zinc are basically ready to shift to the right or influence electrical potential through the circuit. What do I mean by shift to the right? Well, if I basically think of electrons being lost from zinc, then I can say I have my zinc solid in equilibrium to form zinc 2 plus and 2 electrons. If I think of my copper solid, again, wanting to form copper 2 plus, then I have my copper solid in equilibrium to form copper 2 plus aqueous plus 2 electrons. And I'm saying that when we break or open the switch, right, then what ends up happening is we normally do not see copper solid wanting to form the copper 2 plus ion. But we do see that the zinc solid loves to form the zinc 2 plus ion. And therefore, zinc has the ability to want to shift to the right a lot in this overall little equilibrium equation. So if it shifts to the right, that means it's going to be shifting to form more of its ion here. Copper doesn't shift that much to the right, so then we're seeing copper mainly going to stay in its solid form. So just by opening the switch, it basically verifies to us that, hey, zinc is readily available to lose electrons way more than this copper, and so it's definitely going to have a lot of electron energy to push through that circuit. Okay, folks? Now let's talk about when we close the switch. So closing the switch is going to prompt electrons to actually flow from zinc all the way to the copper cathode, right? And this is going to happen, and of course, a voltage is going to be figured out. And then if you have a voltage, your electrons are going to continue to flow until you even out that potential energy. Now, of course, that shift to the right from zinc to copper, for example, is going to be restored. That outflow of electrons, for example, is going to be restored by our salt bridge, just like the copper 2 plus that is leaving solution over here is going to be restored by our salt bridge ion as well. So the spontaneous ability for these electrons from zinc to go to copper and then copper 2, of course, accept them and to form copper solid is all based on the differing ability of zinc and copper to give up their electrons. which we identify zinc as being the stronger reducing agent. So when we start thinking of the how and why the cell works, well, the how is definitely going to come from the construction of the voltaic cell, right? And the why is going to come from the reducing abilities of the metals. So we know that this copper is definitely going to form a solid because it doesn't like to be in its ion form. And we also know that this zinc is definitely going to give up electrons more readily. And so that helps us understand why the flow of electrons is the way it is, on top of us understanding the construction, forcing it to go from left to right as well, based on the anode being negative and the cathode being positive. The first part of the voltage cell jitsu is complete. For the second part of the voltage cell jitsu, let's meet a new member of the village to talk more about voltage itself, or cell potential, and its associated calculations. See you there.